Hello and welcome. Today, we're diving into the fascinating field of paleoepidemiology, essentially, the study of ancient diseases. Forget dusty textbooks. This is about piecing together the health history of humanity using clues left behind centuries or even millennia ago. Paleoepidemiology goes beyond just diagnosing a single ancient skeleton. It looks at how diseases affected whole communities and populations before written records even existed. So, how do scientists become disease detectives for the past? A big part involves looking directly at human remains. Bones and teeth hold incredible stories. Certain marks, lesions, or deformities on skeletons can point towards specific diseases like tuberculosis or leprosy. Ever heard of cribra orbitalia? Those porous spots in the eye sockets can suggest anemia, perhaps linked to poor diet or parasites. Teeth are equally revealing. Lines or pits in the enamel tell tales of interrupted growth during childhood, possibly due to illness or malnutrition, while cavities give clues about diet. But it's not just about the bones themselves. The archaeological context is vital. How were ancient settlements laid out? High population density and poor sanitation would obviously make it easier for infectious diseases to spread. Researchers examine old waste dumps, water sources, and farming techniques to reconstruct the environment and understand potential breeding grounds for pathogens or the insects that carry them. Even burial practices can offer hints. Mass graves, for instance, might signal a devastating epidemic. The real game changer in recent years has been biomolecular analysis. Scientists can now extract ancient DNA or aDNA directly from human remains. This allows for the positive identification of the culprits, the actual DNA of pathogens like Yersinia pestis, the bacterium that causes plague, or the mycobacteria responsible for tuberculosis and leprosy. We can even sequence the genomes of these ancient microbes, tracking how they evolved, spread across the globe, and perhaps became more or less dangerous over time. This helps us connect disease spread with historical events like migrations and trade routes. Alongside DNA, proteomics, the study of proteins, offers another powerful tool. Proteins sometimes survive longer than DNA and can also identify pathogens or reveal how the person's immune system responded to an infection. Then, there's stable isotope analysis. By measuring different forms of elements like carbon, nitrogen, and strontium in bones and teeth, researchers can reconstruct diet, nutritional health, and even where a person grew up or moved to. This helps link health conditions to lifestyle and environment. Ultimately, paleoepidemiology works best when it combines all these approaches. Imagine finding plague DNA in skeletons. That confirms the disease. Then, discovering those skeletons in a mass grave points to an epidemic. Add skeletal signs of previous malnutrition, and you start to understand why that population might have been particularly vulnerable. Why does studying ancient diseases matter today? It gives us a long-term perspective on the constant dance between humans, germs, and our environment. We can see the historical roots of diseases that still affect us, understand how big changes like the switch to farming or the rise of cities impacted public health, and learn about human resilience and vulnerability over vast stretches of time. By looking back, paleoepidemiology offers valuable context for tackling the health challenges we face right now.